In this episode, we are going to explore one of the most important questions in mathematics. When can we interchange the limit and the integral? In other words, when is the integral of the limit function equal to the limit of the integrals? To get what we want, we must first understand what we don't want. This change of perspective will allow us to discover the different phenomena of mass loss, but also a fundamental restriction that governs integration theory. And by the end of the video, thanks to what we will have learned, we will see how to naturally and intuitively reconstruct some classical convergence theorems. To interchange limit and integral, we must make sure that the integral of the limit doesn't differ from the limit of the integrals. But there are two ways in which they can differ. The integral of the limit can be either strictly greater or strictly smaller. For the case of strict inequality, there are three possible scenarios when dealing with non-negative functions. And let us say right away that we will only study such functions here. The first scenario is what we call escape to infinity. To illustrate this phenomenon, let us consider a sequence of functions defined as follows. Fn of x is equal to 1 when x belongs to the interval from n to n plus 1, and Fn of x is equal to 0 otherwise. Here is the graph of the function f0, then that of f1, and so on. As you can see, each function fn is represented by a graph that coincides with the x-axis, except on one interval where it forms a plateau of height 1. As n increases, this plateau moves to the right and is ejected towards infinity. Intuitively, this means that the sequence of functions fn converges pointwise to the 0 function. To prove this rigorously, let us look at the sequence of real numbers fn of x for some fixed real number x. Say x is equal to 4.2. The term f4 of 4.2 is equal to 1 because 4.2 belongs to the interval from 4.2 to 5, and all the other terms are equal to 0. In particular, all the terms are 0 from index 5 onwards, so fn of 4.2 converges to 0. That same reasoning works for any non-negative real number x, which means that the sequence of functions fn converges pointwise to the 0 function. In other words, the limit function is the 0 function. Now let us go back to the integral. The integral of f0, which corresponds to the area under the graph, is equal to 1. We can think of this integral as the mass of the function f0. As n increases, this mass remains unchanged. Indeed, the integral of every function fn is constantly equal to 1. So the limit of the integrals is 1. But since the limit function is the 0 function, the integral of the limit is 0. So we find that the integral of the limit function is strictly smaller than the limit of the integrals. There is a phenomenon of mass loss in the limit, made possible here by mass escaping to infinity. There are still two other mass loss phenomena, which we will present more quickly since the arguments are quite similar. The second mass loss phenomenon is what we will call horizontal spreading, or just spreading to make it short. To illustrate it, we now consider a new expression. For the first function, we get the same kind of graph as before, and the integral is still equal to 1. Then the plateau of the next functions becomes lower and lower, while spreading over a wider and wider interval. But the value of the integral remains unchanged. As in the first scenario, we again obtain that the limit of the integrals is 1, while the integral of the limit is 0, since the limit function is once more the 0 function. This time, the mass loss is caused by the horizontal spreading. Finally, the third phenomenon is called concentration of mass at a point. The expression of the functions may sound complicated at first look, but the idea is pretty simple. Each fn is just a piecewise affine function whose graph is obtained by connecting the origin to the point with coordinates 1 over nn, then to the point with coordinates 2 over n0, after which the graph coincides with the x-axis. The integral of each function is the area of a triangle, so it is equal to 1/2 times the base times the height, which gives 1. We can visualize the graph of f1, then of f2. As n increases, the mass is stretched vertically and collapses onto the origin. Once again, the limit of the integrals is 1, and the limit function is still the 0 function. Be careful not to imagine that there is some kind of Dirac mass, with the vertex of the triangle going to infinity. That is not the case. The integral of the limit function is once again 0, so we still have a mass loss phenomenon, this time caused by concentration of mass at a point. To sum up, we have identified 3 possible mass loss phenomena for non-negative functions: escape of mass to infinity, horizontal spreading of mass, concentration of mass at a point. Whenever one of these phenomena occurs, the integral of the limit differs from the limit of the integrals by being strictly smaller. At this stage, it would be natural to think that the difference might also come from some sort of mass gain. But in fact, this is impossible. You are probably familiar with Lavoisier's famous quote about the conservation of matter. Nothing is lost, nothing is created, everything is transformed. Well, in integration theory, the slogan is rather, nothing is created, everything is lost, everything is transformed. This impossibility of creating mass is a consequence of Fatou's lemma, a fundamental result from Lebesgue integration theory. For non-negative functions, mass cannot be created. In this part, we're going to see how one can build one's own theorems from the ideas we have developed so far. We now know that there is either mass loss or mass conservation. In other words, if there is no loss, then there must be conservation. And this principle underlies the vast majority of integration theorems. They introduce assumptions that rule out the 3 mass loss scenarios. For instance, to prevent escape to infinity and horizontal spreading, it is enough to assume that the domain of definition of the functions fn is bounded. We may then take the functions to be continuous on a closed interval from a to b, which also has the advantage of guaranteeing that the integrals exist. There remains one more assumption to introduce, namely one that prevents the concentration at a point. We need a condition that forbids the formation of the sharper and sharper peak that appears in the third example. A natural idea is to require that the functions fn remain inside a tube centered around the limit function. And this is exactly what uniform convergence guarantees. If this is not clear, I invite you to go back and watch the first chapter of this series. The theorem we have just reconstructed is the following. If the functions fn are all continuous on a closed interval, and if they converge uniformly, then we are allowed to interchange limit and integral. This is precisely the theorem on integration under uniform convergence, which in fact remains valid even for functions that are not non-negative. There is a second way to reconstruct an integration theorem, knowing that we always have either mass loss or mass conservation. If we want equality, it is enough to impose assumptions leading to the reverse inequality. So we should try to impose conditions under which the limit function is above all the functions fn. A natural idea is to require that fn be an increasing sequence of non-negative functions. Be careful. We are not assuming that each individual fn is monotone. We are only assuming that their graphs lie one above another. Under this assumption, we can first justify the existence of the limit function by the monotone convergence theorem. Moreover, since the sequence of integrals is increasing, we also obtain the existence of the limit of the integrals, again by the monotone convergence theorem. Since each function fn is bounded above by the limit function, the integral of fn is less than or equal to the integral of the limit function. Because the quantity on the left has a limit, and the quantity on the right is independent of n, we may pass to the limit and obtain the inequality we wanted, namely that the integral of the limit function is greater than or equal to the limit of the integrals. To sum up, it is enough to assume that the functions fn are non-negative, and that the sequence is increasing in order to interchange limit and integral. Of course, in order to integrate the functions fn, we need an additional regularity assumption, for example continuity. Though for those who have learned a bit of measure theory, you might know that the right assumption is measurability. What we have just reconstructed in a natural way is precisely Bepo-Levi's theorem. Let us conclude this video by emphasizing 2 points. The first point is the method itself. Studying what we don't want is often essential when trying to make a mathematical theory your own. You need to understand what fails. The second point concerns the dominated convergence theorem, a central result whenever one wants to interchange limit and integral. It was not mentioned in this chapter because it will in fact be the main subject of a chapter of this series. If you enjoyed this video, make sure to like, subscribe, and I'll see you in the next one.